And howdy there, Calculus 3 students. We are looking at center of mass today. We're going to start off with just the algebra of center of mass and pretend we have some sort of seesaw in order to get that center of mass, which is, we know that we have this relationship, and we could say that that center of mass relationship was some m1 x1 minus that center of mass equals m2 times x2 minus that center of mass, and then just solving for x bar, or that average value, which would be our center of mass. This is what we would get. And it doesn't really matter if we have 2 objects, 3 objects, whatever. We can have several objects, and those objects in a line would just be the sum of those each mass times his distance from that particular point over the total of the masses. So what we're going to do here is we're just going to figure out what this distance is from a certain focal point, and we'll get that center of mass relationship. So I'll go ahead and write all these things down. Alright, here I have these written down. This is my m1 and that distance from that focal point. And notice that everything on the left has a negative value in distance and everything on the right has a positive value, so this is directional. For that center of mass you will get 1 over 60. And so that means that that center of mass is just a little bit to the right side of that 0, which is, they drew this dot there. Alright. Now we're going to look at center of mass, where the density is changing as we go along that x. So we're going to have a density equation for that we're going to have to deal with, and that's going to change this center of mass. So this capital M we're going to call moment, and our moment is going to be equal to x times that density equation, and we're going to integrate with respect to x, and our mass is going to be that density equation evaluated with respect to x with those limits. And in order to find that center of mass, which is our x bar, it's going to be our moment divided by that mass. So let's see what we've got here. In order to find the center of mass of the bar, I'm going to first have to find both moment and mass. So my moment is going to be the integral of x times that rho, which is 1 plus x squared dx, and that is evaluated from 0 to 2, and I'll integrate that. I will write down that my mass equation is just going to be my density, which is 1 plus x squared integrated with respect to x, and those limits of integration on that are again 0 to 2. I'll integrate both of those two, and then when I get those two values I'll just take that ratio, and that will be my center of mass. Alright, my moment is equal to 6, my mass is equal to 14/3. My center of mass will just be that moment divided by the 14/3, and with that I will get 9/7, and that will be my center of mass. Now we're going to be looking at center of mass in two directions, in 2 dimensions. So what it will be is a coordinate point. We'll need to find the center of mass in the x and the center of mass in the y, and we will have a coordinate point for that. This is called a centroid. That's what we'll be looking for. So anytime you're asked to find a centroid, you're actually finding the center of mass. It is the same kind of calculation. The center of mass is going to be the moment divided by the mass, but in this case it's going to be the moment with respect to y, and my y coordinate point is the moment with respect to x, each divided by that total mass. So let's look at what we have. First thing you'll need to do is draw this. So this one is drawn for you. Here's my upper curve. Here is my lower curve. And I'm going to be trying to find this centroid with the x-coordinate and a y-coordinate. So let's go ahead and look for the x-coordinate. And that's going to be 1 over your mass. So it's going to be y over little m. Let's just go ahead and find my, and then we'll find little m separately, and then we'll just put it together. That's how I think I'd like to do this. So let's do my. So that's going to be, it's a double integral. It's going to be with respect to y and x. I'm going to need x and then times my rho, and my rho in this case, let's see, oh, it has a constant density, so I don't have to worry about that. That's nice. Because it's a constant density, that would be 1. If they gave me a density formula, then I would plop that in right there. I'm going to do this with respect to y on the inner, and then with respect to x. That'll make it easier because my curves are given in terms of y equals. So I'll write down the top one, which is e to the minus x minus 1/2. The lower limit is 1/2 minus e to the minus x. And in order to get what the x is varying from, I'll need to know where these two functions intersect. And if you'll find where they intersect, you just set them equal and solve for that x value. You will find that they intersect at natural log of 2, and they're telling me that, let's see if they tell, oh, bounded by the y-axis, so that's how they tell me this would be a 0. Alright, so I'll do that integration. Alright, after using integration by parts here, you will get, this is your exact value for the moment, and this being your approximate. Then you would perform the same sort of integration for mass, and I get 1 minus natural log of 2 is my exact. For my x-coordinate point, I would do the moment of mass with respect to y, which would be that 0.067 over the 0.307, and this x-coordinate is then 0.217. Next thing I need to do is get that y-coordinate point. However, if I notice the symmetry of this particular shape, I can see that whatever is on the top is on the bottom, and because I have a constant density, I can say that this centroid will be along the x-axis, so that y-coordinate point would be 0. You can go through the motions and get that value, but what you'll end up with is a 0, so this coordinate point would then be 0.217, 0. And that would be your center of mass, or your centroid. I now have a variable density plate, and my density is 2 minus y would be the value for that, and you can see by the shading how this density varies. So I can look at the symmetry of this and once again notice that because of the symmetry, and it's the same on either side, the x-coordinate point is going to be a 0. So I'm going to make it easy on myself and just go ahead and say the x-coordinate point is 0, and I won't solve that, but you could go through the motions of it. I will have to go through the motions of the y to see exactly how high it is up on this y-axis. So I'm going to say that the mass is this double integral, and I need my density equation in here, which is 2 minus y, and this would be dy dx. The y values, they tell me, vary between 0 and 1, so I'll plop those in. The x values they give right here vary between -1 and 1. I believe they have a missed print there, so we'll get that out of there. And I'm going to compute this integral and get my mass. Then for my moment with respect to y, it's going to be another double integral, but and the one with respect to the, oops, I don't mean y, I mean x. So that's what I need to do when I need the y coordinate point. You find the moment with respect to x. That means I'm going to have y times 2 minus y, which is my density equation, dy dx, with those same limits of integration, 0, 1, -1, 1, and I'm going to solve these integrals. Alright, my y coordinate point is then the moment with respect to x divided by the mass. That is going to be 4/3 over 3, and this is going to be 4/9. So my coordinate point is then 0, 4/9, and wherever that would be, let's see, we'll say about in there somewhere. Alright. Of course, now we're going to extend this to 3 dimensions. And very similar, we're just extending this in 3 dimensions. Notice that my x coordinate point is just the moment with respect to y and z, and you would take that density equation and integrate with respect to x, y, and z, and likewise for the other coordinate points. So let's look at this center of mass with constant density. Oh, that makes it nice. Center of mass with constant density. I've got this cone is bounded by, or its height, it's actually this 4 minus x squared plus y squared, and we could integrate with respect to x, y, and z, but let's just use the symmetry of this and notice that because it's a constant density, because this is a cone, the center of mass on the x-axis is just going to be in the middle of that x at x equals 0. Likewise for the y, and the center of mass is just going to be somewhere along this z-axis. So what I'm really looking for is this point right here. And if I can get that point right there, that's all I need to get this center of mass. I could do this in cylindrical coordinates, and that would make my life a lot easier, because you will notice that this right here is just r. So I could write down that z equals 4 minus r. So let's go ahead and find this moment, x, y, and that will get me my z value, and that'll be over my total m. So I'm going to need to find moment x, y. This is going to be a triple integral, and it will be z and then dz, r dr, and then d theta. Alright, so let's play. My z is going to vary between 0 and this 4 minus r. 4 minus r. My radius is going to vary between 0 and 4. My theta, it goes all the way around, so it varies between 0 and 2 pi. And this is much easier now. So let's just integrate. Alright, now let's get the mass. Mass of a cone, I know that formula, and that is pi r squared h over 3. And plugging in these values of pi, and the radius is 4 squared times h. The height is 4 over 3. The mass in this case is 64 pi over 3. Then, in order to get that z bar, that's going to be mxy over m. So that's 64 pi over 3 divided by 64 pi over 3, which equals 1. So the center of mass is at 0, 0, 1. All right. Of course, our next one, we're going to have a variable density varying at this particular function. So first up, I'm going to need to find my mass. That's going to be a triple integral. They've given this to me in terms of spherical coordinates. This means that I'm going to have my density equation in there, and then I will have rho squared sine phi d rho d phi d theta, and I'm going to need my density equation in here, which is 2 minus rho over some value of a. Now I have to figure out what this rho varies from, and this rho is going to vary from 0 to a, and my phi varies from 0 to pi over 2 again, and then my theta, of course, is my favorite, 0 to 2 pi, because it goes all the way around. And I'll compute this integral. Okay, we have the mass, and due to the symmetry of this object, I can see that once again my x and y, the center is going to be on both the x-axis and the y-axis, and therefore we're just going to be looking for that z value, or the height of this. So we're looking for, once again, that value. So for our moment, we are looking for the moment xy, and we're going to integrate again. It's a triple integral, and it's going to be z times our density equation, and my z, I need to write that in terms of my rho, and so that means instead of z, I'm going to be writing this rho cosine phi by definition of spherical coordinates, and then my density equation, 2 minus rho over a, and then it's just going to be the same as the other, rho squared sine phi d rho d phi d theta, with the exact same limits of integration that we found before. Then we'll compute this integral and then get the ratio for z, because z bars, oops, that's not a bar, z bar is going to be equal to the moment with respect to xy over that mass, and we'll get that and compute that value. Alright, after computing those integrals, here's my mass, here's my moment. Plugging in here, I'll get 3 pi a to the 4th over 10 divided by 5 pi a cubed over 6. And when I crunch all of that, I'm going to get that is 9a over 25. And therefore, I can say that this z value right here, oops, is then 9a over 25. And that concludes this section. If you have any questions, please see me at the Collaborate or email me. Thank you.